The main point of this lab is to find the mass of a black hole through its effects on a nearby star, given that star's mass and position points. To find this, Newton's second law and Newton's law of universal gravitation will be used for calculations. Assuming the gravity from the black hole is the only force acting on the star, delta T is 86,400 seconds, and that the mass of the star is 2.7759 e to the 27 kilograms, I found that the mass of the black hole to be equal to 5.202 e to the 31 kilograms. How did I solve this? I had the help of a computational model in Python. First, I input my given values into the initials of the Python model, including the mass of the star, the delta T, and initializing T to equal 0 in the beginning. I also had the model read the spreadsheets given to us of the star's location over time. Then, to find velocities, I used the equation for velocities based on position, but I found them in x and y components, making up the velocity vector. I calculated the x component of the velocity by finding delta x equal to the x final minus the x initial, and then I found the velocity by putting delta x over delta t. I then did the same thing for the y component of the velocity. We then used Newton's second law to find the net force acting on the star and its components. To do this, I found the initial velocity vector and the final velocity vector, and then plugged that into Newton's second law in order to find the net force. I plugged in the final velocity equal to the initial velocity plus F net over mass times delta t, which is Newton's second law. I then turned this into the change in momentum is equal to the net force times delta t, which means that the change in momentum over the change in time is equal to the net force, or dp dt is equal to F net. I plugged this in to Python. In order to find the parallel component of F net, I had to find the unit vector of the momentum. I then had to find the magnitude of delta p over delta t, which is equal to the magnitude of the momentum final minus the magnitude of the momentum initial over delta t. In order to find the dp dt in the parallel direction, I multiplied the magnitude of dp dt times the momentum's unit vector. And we also know that dp dt perpendicular, or the F net perpendicular, is equal to the total net force minus the net force in the parallel direction. I chose to calculate the mass of the black hole at the last calculation, when time t was equal to 94,521,600 seconds. However, any time would work for the calculation, since the net force is mostly constant for the whole orbit, and thus will give the same mass of the black hole. Here's what the model looks like when it is run. Now that we have the net force on the star, we can find the mass of the black hole by using Newton's law of universal gravitation, which is as follows. Newton's law of universal gravitation states that the force due to gravity is equal to the gravitational constant g times the mass of the star times the mass of the black hole over the radius between the two squared. In order to find the black hole, I plugged into Python that the mass of the black hole is equal to the force due to gravity times, or the net force that we found earlier, times the radius squared over the gravitational constant times the mass of the star, which you can see right here in my equation. Though we can see from Newton's law that dp dt is equal to the net force, the two still represent different things. The net force represents the total pushes and pulls on the object, which in this case includes gravity from the black hole. dp dt is the observed rate of change of momentum of the object, or the observed effects of the net force over time. It is important to discern the two. Moreover, the solution I found for the mass of the black hole is unique only to the givens. If the black hole were to be replaced by a black hole of different mass, but all the givens remain the same, I would have found a black hole with the same mass, instead of the mass of the new black hole. However, if the star's position over time did change due to the new black hole, I would then be able to find the mass of that black hole. In all, this lab explored how to use Newton's second law and law of universal gravitation in the real world, and how to analyze the motion of an object when the net force is not zero and causes the object to curve.